applied research engineer at LinkedIn. So he has completed his BTech in computer science and engineering and graduation from NIT Uttarakhand and masters in computer science and automation from IISc Bangalore. So welcome, Ansari. So now session is over to you.
Yeah, thank you, sir, for introduction. So hi everyone. As the sir has introduced, I'm currently working in the capacity of applied research engineer at LinkedIn, and I did my masters from the Indian Institute of Science, Bangalore, and since then I have been working constantly on the reinforcement learning. And while doing my masters, also I worked on a couple of projects on the reinforcement learning, and we did it with a startup, and that's on the real life application itself. Uh, so I'll be starting with the presentation. Yeah. The scope of the today's presentation will be starting with the introduction, in which we'll be going through the AI and its subsets. Then we'll see the basics of RL, the basic framework and how the RL works. Then we'll see some examples in the real life, that closely resembles with the RL. After that, we'll move on to the fundamentals, where we'll explore the key terminologies, and we'll see some basic RL algorithms that will give us a big picture of what are the kinds of algorithms that are there in the RL. And then we'll move on to another important aspect, that is exploration and exploitation. So that is crucial to the RL. After that, we'll move on to applications, and we'll primarily see the applications of RL in the gaming and in the autonomous vehicle. And we'll also understand how the RL is applied to the chat GPT. Uh, After that, we'll see what are the current challenges that are there in the RL. And so this will give you a picture where what are the limitations of the RL are. And uh, that will conclude with that. So starting with the AI and its subsets. So artificial intelligence, if we talk about, it's mainly associated with anything where intelligent agents are involved. So this intelligence need not to come from only data, but it could be coming from the different rule-based system also, or the knowledge-based engineering. And so AI is a big landscape, of which the machine learning is a part. And in this picture, we can see where the reinforcement learning actually fits in the whole paradigm. So artificial intelligence is anything dealing with the intelligent agents. Within the artificial intelligence, there is a machine learning that deals with the usage of data. So we have a lot of data, and we perform a number of uh, tasks on that data. So it involves supervised, unsupervised learning. Supervised learning, where we have the data as well as we provide some additional information in the form of labels, and agent learn from it. And in the unsupervised, we do not provide the labels, but we try to understand the underlying patterns in the data and use those patterns to make the intelligent decisions. Now, coming to the reinforcement learning, in this we do not use directly the supervised or unsupervised learning. It is rather a kind of learning that comes from the repeated interaction with the data. So, for example, in the supervised learning, we just provide the labels, and then we train the model using some algorithms, and we then try to predict the new labels. While in the reinforcement learning, it is just like a sequential decision making problem. So after every action, you need to take the another action, and it is a sequence of action that you need to take. So we'll see how the RL works. So in a broad picture, like RL is something that falls within the machine learning, but it is neither supervised nor unsupervised. It is a kind of learning that is derived from the repeated interaction with the data. Uh, now, let's see what RL actually do. So in this diagram, we can see there are different component of it. One is the agent, another is the environment. There are action, reward, state. So consider a system like where we want the agent to learn a specific thing. So as I told, RL is all about the sequential decision making problem. So agent is someone who will make the decision. Uh, so he is the decision maker, and environment is something where he will take the action. So when we say the decision, it is basically the action, and action, there should be something on which the action need to be taken. So it is the environment on which it will take the action. Now when we come to the environment, it is not just the outer world. It is any information like that reside outside the agent is environment. So when we talk about the RL, it is just like the real life scenario where human is the agent, and uh, everything outside the human is the environment, and human is continuously taking the action, learning from it. So it is the like RL is the closest form of learning that resembles to the how human act. So when we talk about the agent takes some action on the environment, and whenever the agent take an action on the environment, it lead to some change in the environment. Now good or bad, how do we see that change? It is decided by the reward. So reward varies according to what we want to learn. So when we take an action on the environment, it lead to some change in the environment. Now agent again observe the change in the form of reward, like okay, this is the reward I'm getting for the action I'm doing, and then it improve itself over the time. Okay, like last time I did this and I get a negative reward. Now reward could be negative as well as positive. If the action is good, it will give a positive reward. If the action is bad, it will give a negative reward. Now the agent sees the reward and uh, improve itself to get the positive reward next time. So it's a cycle of it runs in a cycle. It first observe the state, then take the action, and then observe the reward, improve itself, and reward and change the state also both are observed. So change the state, then again it take the action. So this is like a basic skeleton of the reinforcement learning. Reinforcement learning is all about this whole diagram. Now coming to the real life examples of the reinforcement learning where we can closely relate to. So consider the example of learning to ride a bicycle. So remember when we first time started riding the motorcycle, like this bicycle, when we pedal, the cycles turn right, like it began to fall. Then we understand, okay, we receive a signal from that. Okay, this is the action we have taken. We have tried to pedal, and the cycle is falling in this way. So we adjust our weight according to that. So next time we pedal, we also adjust our weight also, so that cycle do not falls. And in this process of repeated interaction, you take the action. Here action is pedaling. Now the environment is your cycle or the road on which you are walking, and your improvement is like you as an agent is improving yourself in every iteration to adjust the weight. So you pedal as well as adjust the weight of your body so that cycle do not fall. So this is the like form of reinforcement learning that we are doing. We are learning from the reward. Now consider another example of training a pet. Here the agent is the pet. So when you say let's you are training a dog, you ask him to sit down. So if he sit down, you give him something like a biscuit or food. So now the dog understand, okay, when this person make the sound like sit, So if I sit, I'll get a reward. So next time you say sit, he will sit because he's getting the reward. And let's say if you say sit and he run away, he do not get the reward. So over the time he understand that if I sit down, I will get a reward. So it is a form of reinforcement learning. Similarly, it is the example of the writing. So when we try to write a letter, we try to copy it, and the child, it is trying to draw it. So it draw the letter and see, okay, this do not look like the original letter I intended to draw. So it draw again. So it received the feedback in the form of like the comparison, like how good this letter it has written is. So over the several iteration, it began to understand that okay, this is the like correct way of writing the C, and over the time it will improve. Next, we'll move on to the key terminologies that are there in the RL. Uh, so we see several examples also where we get to know the working of the RL. Now, there are some names assigned to each of the entity involved in the RL, starting with the state. So, as we have seen the environment, so every information that is required to take an action that lies in the environment is a state. So when the agent observe the environment, it essentially try to get the state out of the environment. So it essentially observe the current state of the environment, and state consists of any information that is required to take the action. Action is something that we wish to learn, that the agent is trying to learn, that it will perform on the environment, and that will lead to the change of the state. Now, reward. So it is highly specific to the task we are trying to learn. Let's say you want to learn the bicycle. So here the reward is like if the bicycle is running, not falling. So that is your reward. Now, in a different scenario from the perspective of a dog, so reward is something like food. So reward is highly specific to the action we are trying to learn, and so agent take the action and observe the reward, whether he get the positive or negative reward. Based on that, it improve itself. So we got the state, we got the action, we got the reward. Now policy is something like policy is uh, accumulative behavior of the agent, using like through which it takes the action. So let's say same action is not best in every scenario, right? So when it observes the state, based on that state, it takes a certain action. Now there are many states, and each state is different. So we and our agent is a nothing but a mathematical entity. So when we say the let's say it is making some policy, so it is accumulating the experience and trying to learn a function that will tell it what is the best action in a given state. So the goodness of the action is determined by the reward. So essentially, policy is something that tells the agent what is the best action it should be taking in that state, so that it lead to overall high reward. Uh, Now the last term is the value function. So it has to be mentioned here because it will come forward. So value function is something that tells the agent how good an action is. It essentially assign a value to uh, the tuple state and action. So it could be the value of a state itself, or it could be the value of a state action itself. So value function is essentially, let's say you observe the state, and in this state you want to know how good the action is. So you there's a value function that we try to learn uh, for a given state and action, and it tells us, it gives us a value that demonstrate like how good that particular action is in this state. So moving on from the terminology to the framework. So this is similar to like what we have already discussed. So at a given time t, so agent observe the state st. Now, based on the current state st, it takes the agent this action 80. Now, when the action 80 is taken on the environment, it changes the state from st to st dash, and environment emits a reward rt, and then the agent update its policy according to that reward value. So this is the complete cycle of the RL framework. Now, when we talk about the like we have discussed the basic framework of the RL. When we talk about the learning, it has to be based on some algorithms. So how do we do that? Like if you look at the previous diagram, so agent, we say that it receives a reward and then it improves the policy, like it updates its policy. Now the policy, when it updates the policy, it has to be according to some algorithm. So there are different kind of algorithm that exist in the RL, and they all play part here. As soon as it observe the change in the state and the reward, the algorithm try to improve the policy. Now, there are two major categories of the algorithm. One is the value based, another is the policy based. Uh, so, value based, as I told, like there is a value function that we uh, try to learn over the time that tells us how good action is in a given state. So, the algorithm falls into two broad categories. One is like if you see logically, if we have, say, a value function with us, then we can take the action according to that value function, right? Let's say value function is giving me the value corresponding to every action in a given state. So let's say there are three actions, 1 2 3, and according to like the value function, the value corresponding to one is 2, then 2 is 5, and the 3 is 1. So the here the best action is the 2, so I will take the action. So in the value based learning, we try to learn the value function that correctly tell us, like for a given state, what is the value of different action we can take. Coming to the policy based learning, we skip the value, like value function, and we directly try to learn the policy. So policy is something based on which we take the action. So policy is nothing but a probability distribution. So we try, yeah, yeah.
Sir, so what is the difference between a policy and value function?
Yeah, I'll tell. So when we talk about the value function, so it is like there are different actions, and we are trying to get the value of each of the action. How good we are evaluating the different actions. Like okay, this action is this good, and we can choose from this these available set of actions. Now, when we are coming to the policy based learning, it is giving us the probability distribution, like for a given state, this is the probability distribution of action that need to be taken. So now you do not have value corresponding to a particular function, a particular action. Rather, you have a probability distribution according to which you will sample the action. So you don't know the underlying value, but you are sure that this distribution, if I sample according to this distribution, then I'm going to maximize my cumulative reward.
So is it like I can say one hot encoding and probability distribution like that? It's a particular one value regarding to the function, and it's kind a set of functions, and we are getting the probability distribution.
Yeah, kind of that.
Okay, sir. Thank you.
So these are the broad umbrella of the value function and policy based. Yeah. So now the examples are like of the value based function is the Q learning, and the policy based function is the policy gradient method. Like in the uh, Q learning, we essentially try to model a mathematical function that give us the that depicts the value function. And in the policy gradient method, we like try to model it as a maybe a neural network or some other uh, approximation function to that give us the distribution. So now one thing to observe here is uh, one thing that is crucial to reinforcement learning is exploration and exploitation. So we have just learned that we over the time we try to understand like what is the value of different action. We try to learn the value function that gives us the value corresponding to different action. Now consider the case like in the real life scenario, there are many actions that are possible. Let's say like these are the different actions, d1 up to d5. So let's say you start learning, and reinforcement learning is all about learning with the interaction. So you start learning, and so far you have taken the only two actions, d1 and d2. You have not taken any of the remaining action. So when you take the action d1, you observe a high reward. When you take the action d2, you observe a low reward. And for other functions, you have not encountered these actions. So you do not have any idea of what the reward of these actions will be. So now the third time it comes. So according to the value function, since the reward corresponding to d1 is high and d2 is low, so you will choose the d1. Now again, this will keep on happening if you keep on exploiting. So there are two things: exploitation and exploration. Exploitation is when we choose the best action according to the policy we have learned so far, and exploration is choosing the random action. So when we do the exploitation, let's say we have learned the reward function that tells we have learned the value function that tells us a value corresponding to the different actions. Now you will always be choosing the action that gives you the highest value in a given state. But let's say there is some action that you have not taken so far, you don't know anything about that action. uh, if you do not do the exploration, you will never get to see like what lies in the d3. So let's say after some time you do some exploration, you take a random action, and its random action was d4. Now you observe that okay, other actions are also there that can give me high reward. Then another round of exploration, you take the action d3 and you observe d3 as the highest reward. So it to learn efficiently, like to learn the best policy, so exploration is crucial. So exploitation is when we run according to the what we have learned so far, and we take the best action according to that. Exploration is something we try to explore. Now if we keep on exploring, we will always be taking the random action, and that's not a good idea. So what happens is like uh, how to how to balance this thing. So in RL algorithms, what we do, 99% of the time we exploit, like we take the action that is best according to our policy, and 1% of the time we do the exploration. So once in every 100 or once in every 1,000 step, we try to take the action that we have not taken yet, and we see the reward. So with this time, like over the millions of iteration, millions and billions of iteration, we even a fractional exploitation will lead to the emergence of the new policies that will give us the better reward. So this is the all about exploration and exploitation. Now coming to the real life applications of the RL. So we'll be talking about the first application that revolutionized the field of RL. That was the that DeepMind came up with, and AlphaGo is a thing. Then we will see the how the autonomous vehicle take the advantage of RL, and then we'll see the chat GPT application of the RL in the chat GPT. So before let's see a small video about the AlphaGo.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
They said all is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face. That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think something went wrong.
Yeah, it's made him think.
He's got to pronounce America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So yeah, regarding this, a whole documentary is available on the YouTube. So it's regarding the how the AlphaGo defeated the world champion in the game of Go. So in the game of Go, how it works is there are infinite number of states that are there, and so the action is what is the next best action you can take. So it was found that DeepMind came up with the algorithm. It's a very complex algorithm. So it came up with an RL algorithm that was able to learn, it first played the game of Go with the beginners, and so over the time it began to understand the strategies that they are making, and what is the best action. So it is constantly observing the state of the board. It is constantly trying to observe what is the best action, and over the time it became so expert, it became so good at playing the Go that it defeated the world champion. So this was about the AlphaGo. And its introduction, actually the documentary is interesting to watch. They tells everything, how they train and how they set up the competition, and how it defeated the world champion.
Go is
Yeah. So the next application is the RL in the autonomous vehicle. So let's say when we drive a car, let's try to bring the situation in the paradigm of the RL. So when we drive a car, we see what is there in front of us, and we are aware of the how fast our car is moving, and we are aware of the vision in the rear view mirrors, what is coming to the side, what is coming to the left or right. So we are aware of the different things. So we are the agent in that case, and everything except us is the environment. And let's see what are the actions available to us. We can steer, we can apply the brake, or we can accelerate. Let's forget the gear for the time being. Let's say there are two things. One is we can apply the brake and we can accelerate. So when it comes to the autonomous vehicles, so not only the front image and the back image, there are also different sensors available. There are different sensors also, from which we pass on the reading to the algorithm. So as you see in the picture, so we provide the front vision and the reading from the different sensors that basically tells like what is the depth and what is the distance from the like the next thing that is ahead of the car, and we provide the vehicle speed also. Now this is the state for our agent. So every information that is required to take the action to drive the car. Now the set of action available to us is like whether you apply the brake or not, whether like how much to steer. So all these actions are available. So uh, we take all these readings from the sensor and camera, we process it, and we provide it to the agent. That is the state for the agent. Now we have different action available to us. We when the agent sees the reading, it gives us like this much to steer right, and this we need to apply this much of brake, and we need to apply this much of acceleration. So we do that, and we see car moves forward or stops, so according to the action. Now coming to the reward, that is a complex function. How will we decide the reward? Let's say you decide the reward according to uh, car should not hit someone. So in that case, that reward is not a very good reward, because to not hit someone, it will go off the road, because off the road there will be no one. So now you say, okay, keeping on the road is important. So if it goes off the road, we will give it a negative reward. Fine, it stays on the road and do not hit. So it will not move forward. It may not move forward because it will become stationary, thinking that if I move forward, it I might hit something. So then you say, okay, there should be some reward associated with the movement also. So a reward is a complex function, that what I want to convey. Like it's not as simple as like there are a lot of effort go into the reward engineering. Like what should be the correct reward for a given problem. So when we come to the autonomous vehicles, so it's a combination of different factors, like the speed of the vehicle or the obstacle, how it avoids the obstacle, how much the car shakes. So it's a very complex function that that consists of the reward, and this whole complex function is fed to the agent. Like agent take the action, observe the state, and reward come from this complex function, and based on that reward, it improve its policy. So below is a demonstration of like how the car learns to park. So initially it is hitting the obstacle, now it is getting the negative reward, and over the time it learns to park at the right place. Uh, Now coming to the next application, that is in the chat GPT. So I hope everyone has heard of the chat GPT. So that is the like most hype thing that we are seeing today nowadays. So let's understand the working of it, and we'll see how the RL plays an important part in the training of the chat GPT. So what happens is there are three steps that are essentially used in training the chat GPT. So one is like they train all the demonstration data. So it has nothing, the step one has nothing to do with the reinforcement learning. It is purely supervised learning. So we collect the data. Data is in the form of prompt and the response. So they provide a prompt and they fine tune it with the response. So over the time, like after the training, we have a model that give some response according to the given prompt. But when we think about it, so it do not gives always, like it do not acts like human. It is just like we have given it some data, and according to that data it will keep on giving us the answers. Now to make it more realistic, to make it more so this thing had already been used for a long time, and so people were not getting these good results as we are getting from the chat GPT. So these things were like already being done by the people, but results were not so good. So what OpenAI team did, they introduced like okay, we'll apply one more layer of RL on this. So as we have seen, the RL require the state, action, reward, And reward engineering is one of the complex thing that we care about. So what they did, um, they first train, since the reward could be very complex, and like even in the text data it is even more complex. So what they did, they try to train a reward model itself. Okay, let's not define the reward function, we will train the reward model itself. So to learn the reward model, what they did, so they provide a prompt to the agent, like the this pre-trained model, and like output the response. Now they feed it multiple times. The same prompt was feed multiple times, and they collected the 4 or 5 responses of the model. Now they ask some humans to rank these responses, like in the order of how good they are. So they ranked it like a D is better than C, is better than A, and B is worst. So a labeler ranks these output. Okay, yeah, these are the output given by the same model in different iterations, and this is the good output and this is the bad output. Now they train reward model based on this information. Okay, if this is the ranking, then they train a reward model that will give the best reward if it is D, and lesser reward if it is C, even lesser if it is A, and worse if it is B. So they train a reward function that was essentially a deep neural network that takes the prompt and response and gives a reward. Now this is a separate thing they did. Now coming to the original model, uh, they use the PPO algorithm to output the what response it should be getting. Now PPO is a policy-based method of the RL, policy-based algorithm that we see the two umbrellas were there. One is the value-based and another is the policy-based. So PPO is the proximal policy optimization. So this PPO algorithm utilizes this trained reward model to decide, like now they are feeding a prompt to the chat GPT. Now it is outputting the prompt, like it is giving us some output. This output they are feeding to the reward model. Reward model is giving us the reward they are again feeding to the agent, and agent is improving the chat GPT so that it outputs a better it give a better output. So this is the whole cycle that is behind the chat GPT, like supervised training, then training a reward model, and then using the PPO algorithm to fine tune this using the RLHF. This whole process is known as the reinforcement learning from human preferences, that RLHF normally we call. So that is all about ChatGPT. So we can see that the reward engineering is very important. Like in this case, there was no certain way to decide like what should be the reward. So they trained a reward function because a deep neural network can learn the complexities behind this. So they have just the ranking, and they trained a neural network that tells us the reward. And using that reward, they use the RL to again improve the ChatGPT model. Now, RL is not just the few examples we have seen. There are many other things also. Now you'd be able to relate more, relate better in this. So let's say these are the things in the assembly line where, like, how much to rotate this arm, how much to rotate this arm, and then how much to expand and how much to contract. So these all things, like these are the agent, and everything they are observing is the state, like, environment, and they are taking the action, learning the policy, improving over the time. Similarly, RL is like RL is widely used in the industry, in the robotics mainly, like for automating the tasks that humans were doing, and it is performing very good in many industry. So another important application is the reinforcement learning in traffic signal. So during my working at the IC, so my professor was working on this problem for the Bangalore itself. So they see like how we can traffic is a huge problem in Bangalore, and so can we apply the RL to turn on and off the traffic light so that the traffic is minimized. So everything on the the snapshot of the traffic on all the lanes is the state, and action is which signal to turn on and which signal to turn off. So over the time, we had the data and uh, try to learn the policy that can reduce the traffic, according to for how long we need to turn on the green light on this lane and for how long on the other lane. So another example is like a personalized chatbot experience that we see in a daily basis on many websites. So we do some query and then our chatbot replies. So it's a standard NLP problem, but chatbot uses the extensively use the RL to make the responses better according to what the human is responding. Similarly, there are other use cases also, like data center cooling is there. Google uses the data center cooling RL in the data center cooling. So for how long to optimize the power, essentially, like for how long to turn the AC on, how much to increase the temperature, decrease the temperature. So these all kind of thing, like it observe the current temperature and the state, and according to it, it to do the cooling. So these are some real life applications of the RL that we can see on a daily basis. Now there are some challenges associated with the RL. So these challenges are data inefficiency is one of the thing. We see that the RL mainly learns with the repeated interaction with the environment, and it require a huge amount of data. Now consider a situation where each interaction is taking 1 or 2 seconds. In the real life scenario it happens, so each interaction is taking 1 or 2 minutes. So gathering a 1 million amount of 1 million interactions is like 1 million seconds, that is some years, I would say. So that's why it's a challenging problem for the RL. For the cases where the interactions are slow, RL is not very much practically applicable in those cases. But simulation is there to help. For example, in case of the autonomous vehicle, so uh, everything is almost deterministic. When you accelerate, so gadi will move this much forward. If you brake, car will stop after this time in it. So it can be simulated, and when something can be simulated, it can be run on the supercomputer to make it super fast. So that's why autonomous vehicle is one of the successful application of the RL, because simulation exists, and with the simulation we can create as much amount of data as we want. And now similarly, the other cases also, like when we talk about the assembly lines, so that can also be simulated. So that is one of the thing where RL is highly successful. Now there are, however, a few challenges that RL is not able to overcome for the cases where everything is so undeterministic, and we cannot simulate it. So it happens in the healthcare also. For example, when you, let's say you are using the RL to let's say for some diagnosis, so we cannot simulate. It is not very much clear, like if we give this medicine, if we inject this thing into the patient, then what will happen. So we cannot simulate it infinite number of times, and there's no way to simulate it. So that is one of the challenge that we face with the RL. However, there are RL is evolving, and it is coming up with the new methods to mitigate these inefficiencies. Uh, so yeah, so one is the data efficiency is one challenge, and simulation is the answer. But simulation is not applicable in all the cases. But most of the, many of the practical use cases, the simulation is there, and we train the model in the simulation and then use it in the real life, and it works pretty well. So like example, the game is also like you can simulate. We talked about the AlphaGo. There's another improvement over that is the AlphaGo Zero that do not use any human interaction at all. So it played with itself only in the simulation, and it was like better than the AlphaGo. Over the time it get better than the AlphaGo itself. So AlphaGo Zero was like we did not provided it any expert from which it can learn. It just played with itself, like the two AlphaGo Zero agents playing with each other, improving over the time, and they mastered the game. Now another thing is the reward engineering. So as we discussed, like reward engineering is the crucial aspect in the RL, and uh, reward decides like what the agent is going to learn. A bad reward may lead to bad playing. Like for example, when you play the chess, if say you decide the reward, okay, if it wins it's 1, and if it do not wins it's 0. So that is not a very good reward, because no, let's say that is long term reward. Let's say when if we take out the opponent piece, then we give a positive reward, and if it loses its piece, then we'll give it a negative reward. Now this is not a very good reward function, because it will not it will keep on focusing not winning the game, but it will focus on taking out the opponent's pieces. And it might be good for the short term, but not for the long term, because in the process it might lose it will not be able to decide the importance of the pawn and the queen. So it might treat the queen and pawn equally, and since the reward we are giving it is equal when it lose the pawn and when it lose the queen, so it will not protect the queen, and might end up losing in the long run. So reward engineering is very like a complex task, and as well as the most important aspect, because it decide what the agent is going to learn. Now another thing is like generalization is one of the thing. uh, Now when we do the interaction with the environment, let's say the example of the autonomous driving, so it's not possible to simulate all the scenarios. Like you can simulate the uh, traffic on the road, and you can simulate the, let's say, uh, traffic on the let's say hilly area, and where the roads are ups and downs. So but there are infinite possibilities. Like it might face the road where there are only stones, where there is only like a lot of water on the road, where the road is slippery, road is tilted. So all those scenarios we cannot uh, cover all the scenarios. So generalization is the ability to perform well in the unseen scenarios, and uh, RL somehow like it has gotten better, but generalization is sometimes a problem in the RL. Like we have trained, let's say, it on the different scenario, and now it experiences a new scenario, so it do not perform that well, but it performed relatively better, like it performed good actually. But generalization is something we need to take care of. Like we need to have some we need to evaluate it on the different scenarios that we should keep aside to ensure that it is generalized as well. Now scalability is one of the important thing that we face in this. So right now, like if actions are limited it's fine, but if let's say actions are infinite, then how are we going to represent our value function? So we say the value function give the value according like corresponding to each of the action. So it's not feasible to check the value corresponding to, let's say, 1 billion actions, possible actions, and run the model to get the values of those. So to make it the scalable, there are many different like new algorithms that are popping up, and they are basically covering the limitation from the scalability perspective of it. So Monte Carlo research is one of the thing that DeepMind use in the AlphaGo, because in the AlphaGo we see there are many different state, and each state there are many actions possible. So they there are different algorithms that people are coming up with to overcome these challenges. So yeah, that's pretty much it. Thank you, everyone. Any questions you have?